Welcome to Young Measures and an introductory course on Heisenberg groups. In recent decades, Heisenberg groups have become extremely popular in analysis and geometry circles. Indeed, there isn't a conference without a talk or two on the subject. But what are Heisenberg groups and why are they so important? This series of lectures will be trying to answer these questions to some degree. The question of what Heisenberg groups are can technically be answered in a couple of slides, but that barely answers the question of where they come from, why are they so important, and why would someone think of such objects. I've decided that by comparison to the Euclidean space, we can have some overview of its common features. Euclidean spaces are important because they are the basic foundation of Riemannian manifolds. Even if in a hypothetical world we started understanding tori and spheres and other more complicated manifolds, we will still be led to discovery of Euclidean spaces, because even in an intrinsic sense, they are the limits and tangents of Riemannian manifolds. Heisenberg groups are examples of tangent spaces to what is called sub-Riemannian manifolds. The next thing that makes Euclidean spaces interesting is that there is homogeneity. Every point of the space is identical to another point of the space. And this can be made precise by translation of the space. You can translate 0, 0, the origin, to any other point. And under this translation, you can also translate vectors with them. You can translate curves going through 0, 0 in a rigid motion to starting at any other point. The more general construction behind this is that of a Lie group, where a smooth manifold is also equipped with a group action, a group multiplication, which is compatible with the smooth structure. Using the group action, we can also identify vectors from one tangent space with vectors in a different tangent space. And similar to the Euclidean case, we can basically translate any local structure to a local structure at a different base point. Heisenberg groups are also Lie groups. And what makes them a bit more interesting than the Euclidean space is that the group operation is not abelian. In particular, it's not a vector space. For the Euclidean case, the Lie group structure, just to emphasize, is this addition operation as a vector space. Now, we go to metric structure of Euclidean spaces versus the Heisenberg structure. If we equip any smooth manifold with a Riemannian metric that is a dot product at every tangent space in a smooth way, then we can find length of curves and from that construct a metric, a distance function on the manifold. In Heisenberg group, we do a similar construction, except that instead of allowing every possible curve connecting two points, we require that these curves have tangents, have velocities that lie in a certain subspace of all possible directions in the tangent space. Even in the absence of a group structure, this can be done, and this leads to what is called sub-Riemannian manifolds. So Heisenberg groups are also particular examples of sub-Riemannian manifolds, and in some sense, the simplest of them. First of all, they are manifolds with just one chart because Heisenberg group Hn is homeomorphic to the whole space R to the power 2n plus 1. So it's somehow simple in that regard that it has a trivial, or maybe it has a well understood chart map. But then when it comes to its sub-Riemannian structure, it diverges from what happens in the Euclidean case. The last structure is that of scaling. Given a point x, y, z, say in R3, and a positive number r, we have the point rx, ry, rz. I want to emphasize that I'm thinking of this as a point mapping to another point, rather than a scaling of one vector in one tangent space. This operation is compatible with translations in Rn, and also r times a point makes its distance to the origin shorter or longer by multiplying into r. In Heisenberg groups, we have a similar scaling operator, which takes a point in Heisenberg group and a positive number r and produces another number. And this association is compatible with both the Lie group structure, that is, there is some invariance when you translate 2 points and then multiply by r, versus you multiply by r and then translate. And secondly, this scaling works perfectly with the sub-Riemannian metric given to the Heisenberg groups. The role of scaling in Euclidean spaces is actually quite deeper than what we may think. Think about how you define derivatives, say directional derivatives in Rn. You start at the point x, you take the direction v, you multiply rv, you add to the point, and then you subtract f of x, and then divide by r and take limit. This addition and subtraction can be done in Lie group by multiplication and taking inverse. But not every Lie group supports an operation of the type r times a point, the scaling. Carnot groups do, and Heisenberg group is an example of a Carnot group. So the fourth structure, other than being a manifold, a Lie group, and a sub-Riemannian manifold, the fourth structure that makes Heisenberg groups very interesting is that they do support such scaling, from which we are able to define a notion of differentiability due to Pansu. So Heisenberg groups compete with Rn on one hand by having this rich collection of structures. On the other hand, by being non-abelian and by being non-Riemannian, rather being sub-Riemannian, they add that extra twist, which makes the questions more difficult / more interesting. And we will be discussing all of these structures in coming lectures. We will use Heisenberg group as an excuse to introduce the notions of sub-Riemannian geometry and of Carnot groups. So, if you are interested in learning more about Heisenberg groups, please subscribe below so you get notifications of my coming up lectures. Thank you for watching this far, and see you soon in the first lecture on Heisenberg groups.